I'm Philip Meyer, a course developer at Google. Welcome to Networking in Google Cloud Platform. Consider for a second the impact Google Search has on our daily lives with timely and relevant responses. Now, think of other Google products: Gmail, Maps, Chrome, YouTube, Android, Play. Each of these products has over 1 billion monthly users. Google had to develop networking technologies to meet the requirements of a distributed computing infrastructure that can support those billions of users. Google Cloud's goal is to share these innovations and infrastructure with you so that you can also impact and delight your users. We cover a critical piece of that infrastructure, which is the network. This map represents GCP's network from an infrastructure perspective. As of this recording, GCP's well-provisioned global network connects 52 zones to over 100 points of presence through hundreds of thousands of miles of fiber optic cable. Google is continuously investing in this network with new regions, points of presence, and subsea cable investments. On top of this network, GCP uses state-of-the-art software-defined networking and distributed systems technologies to host and deliver your services around the world. The services shown here are a subset of all the services covered in the second and third course. The courses build on each other. Therefore, I strongly recommend that you take them in order. The first course is Google Cloud Platform Fundamentals Core Infrastructure, which I have linked below this video. Defining and implementing networks is the second course. In that course, we start by going over the fundamentals of networking in GCP by focusing on VPC networks, subnets, and firewall rules. Next, you will learn how to control access to VPC networks. Then, we will go over how to share VPC networks across projects. Last, you will explore the different load balancing services in GCP. Hybrid connectivity and network management is the third and final course. In that course, you will first learn about hybrid connectivity among networks. Next, we will cover networking pricing and billing to help you optimize your network spend. Then, you will explore common network design patterns and the automated deployment of networks using Terraform. Last, we will go over monitoring and logging features that can help you troubleshoot your GCP network infrastructure. Now, my goal for you is to remember and understand the different networking services and features, and also be able to apply your knowledge, analyze requirements, evaluate different options, and create your own services. That's why this includes interactive hands-on labs through the Quick Labs platform. Quick Labs provisions you with a Google account and credentials so that you can access the GCP console for each lab at no cost.
However, if you need to define RBAC permissions across multiple databases, then you'll need to use the custom method. There is another older authorization option permitting attribute-based access control or ABAC. RBAC is similar to network than ABAC. Google recommends that you use RBAC to disable ABAC. ABAC is disabled by if you upgrade a custom earlier today, you'll have to disable ABAC.
In this module, we will be covering Google Cloud VPC networking fundamentals. GCP uses a software-defined network that is built on top of a global fiber infrastructure. This infrastructure makes GCP one of the world's largest and fastest networks. Thinking about resources as services rather than as hardware will help you understand the options that are available and their behavior. In this module, we will start by introducing Virtual Private Cloud, or VPC, which is Google's managed networking functionality for your cloud platform resources. Then, we are going to dissect networking into its fundamental components, which are projects, networks, subnetworks, IP addresses, routes, and firewall rules. You will explore GCP's network structure in 2 labs by creating networks and subnetworks of many different varieties, and by exploring the network relationship between them including how to create a VM instance with multiple network interfaces. Let's start by talking about GCP's network, and specifically Virtual Private Cloud, or VPC.
This map represents Google Cloud. On a high level, Google Cloud consists of regions, which are icons in blue, points of presence, or POPs, which are dots in blue, a global private network, which is represented by blue lines, and services. A region is a specific geographical location where you can run your resources. This map shows several regions that are currently operating, as well as future regions. The POPs are where Google's network is connected to the rest of the internet. Google Cloud can bring its traffic closer to its peers because it operates an extensive global network of interconnection points. This reduces cost and provides users with a better experience. The network connects regions and POPs and is composed of hundreds of thousands of miles of fiber optic cable and several submarine cable investments. Here's how Google Cloud is organized. Let's start at the finest grain level, the zone, shown here on the right. A zone is a deployment area for Google Cloud resources. For example, when you launch a virtual machine in Google Cloud using Compute Engine, which we'll discuss later, it runs in a zone you specify. Although people think of a zone as being like a Google Cloud data center, that's not strictly accurate because a zone doesn't always correspond to a single physical building. You can still visualize the zone that way though. Zones are grouped into regions, independent geographic areas, and you can choose what regions your Google Cloud resources are in. All the zones within a region have a fast network connectivity among them. Locations within regions usually have a round-trip network latency of under 5 milliseconds. Think of the zone as a single failure domain within a region. As part of building a fault-tolerant application, you can spread
Hello? Hello?
Think of the zone as a single failure domain within a region. As part of building a fault-tolerant application, you can spread their resources across multiple zones in a region. That helps protect against unexpected failures. You can run resources in different regions too. Lots of Google Cloud customers do that, both to bring their applications closer to users around the world, and also to protect against loss of an entire region, say due to a natural disaster. A few Google Cloud services support placing resources in what we call a multi-region. For example, Google Cloud Storage, which we'll discuss later, lets you place data within the Europe multi-region. That means it's stored redundantly in at least 2 geographic locations separated by at least 160 kilometers within Europe. Next, let's focus on services by starting with Google Cloud's Virtual Private Network, or VPC. With Google Cloud, you can provision your Google Cloud resources, connect them to each other, and isolate them from one another in a virtual private cloud. You can also define fine-grained networking policies within Google Cloud and between Google Cloud and on-premises or other public clouds. Essentially, VPC is a comprehensive set of Google-managed networking objects that we will explore in detail throughout this module. Let me give you a high-level overview of these objects. Projects are going to encompass every single service that you use, including networks. Networks come in 3 different flavors: default, auto mode, and custom mode. Subnetworks allow you to divide or segregate your environment. Regions and zones represent Google's data centers, and they provide continuous data protection and high availability. Vpc provides IP addresses for internal and external use, along with granular IP address range selections. As for global network of interconnection points, this reduces costs and provides users with a better experience. The network connects regions and POPs and is composed of hundreds of thousands of miles of fiber optic cable and several submarine cable investments. Here's how Google Cloud is organized. Let's start at the finest grain level, the zone, shown here on the right. A zone is a deployment area for Google Cloud resources. For example, when you launch a virtual machine in Google Cloud using Compute Engine, which we'll discuss later, it runs in a zone you specify. Although people think of a zone as being like a Google Cloud data center, that's not strictly accurate because a zone doesn't always correspond to a single physical building. You can still visualize the zone that way though. Zones are grouped into regions, independent geographic areas, and you can choose what regions your Google Cloud resources are in. All the zones within a region have a fast network connectivity among them. Locations within regions usually have a round-trip network latency of under 5 milliseconds. Think of the zone as a single failure domain within a region. As part of building a fault-tolerant application, you can spread their resources across multiple zones in a region. That helps protect against unexpected failures. You can run resources in different regions too. Lots of Google Cloud customers do that, both to bring their applications closer to users around the world, and also to protect against loss of an entire region, say due to a natural disaster. A few Google Cloud services support placing resources in what we call a multi-region. For example, Google Cloud Storage, which we'll discuss later, lets you place data within the Europe multi-region. That means it's stored redundantly in at least 2 geographic locations, separated by at least 160 kilometers within Europe. Next, let's focus on services by starting with Google Cloud's Virtual Private Network, or VPC. With Google Cloud, you can provision your Google Cloud resources, connect them to each other, and isolate them from one another in a virtual private cloud. You can also define fine-grained networking policies within Google Cloud and between Google Cloud and on-premises or other public clouds. Essentially, VPC is a comprehensive set of Google-managed networking objects that we will explore in detail throughout this module. Let me give you a high-level overview of these objects. Projects are going to encompass every single service that you use, including networks. Networks come in 3 different flavors: default, auto mode, and custom mode. Subnetworks allow you to divide or segregate your environment. Regions and zones represent Google's data centers, and they provide continuous data protection and high availability. VPC provides
without having to specify and manage those details in each pod definition. What's in a pod security policy? Each consists of an object and an admission controller. The pod security policy object is a set of restrictions, requirements, and defaults that are defined in the same way as the security context inside a pod and can be used to control the same security features. For a pod to be admitted to the cluster, it must fulfill all of the security conditions that are defined in the pod security policy. These rules are only applied when a pod is being created or updated. The pod security policy controller is an admission controller that validates or modifies requests to create or update pods against one or more security policies. You saw earlier in this module that a request to perform a specific action has to be authenticated and then authorized. But there's an extra step called admission control. police context and the available pod security policies. Note that these policies are enforced during the creation or update of a pod, but a security context is enforced by the container runtime. This is an example of a pod security policy. You'll learn how to create a pod security policy in the lab.
After you define a pod security policy, you need to authorize it. Otherwise, it can prevent any policy from being created. You can authorize a policy by using Kubernetes role-based access control. Here, a cluster role allows a pod security policy called demo-is enabled to be used. Next, define a role binding to bind to the previous cluster role to users or groups. In this example, two subjects for the role binding are specified. The first is a group containing all service accounts within the daemon instance. The other is a specific service account in the daemon instance. The role binding group the creator of the pod like a deployment, reset, or any other daemon or rather, the creating pod service account. Granting controller access to the policy will grant access to all pods created by that controller. So the preferred method of authorizing policies is to grant access to the pod's service account. Without a pod security policy controller, pod security policy you need to both define the policies and to enable the pod security policy controller. If you enable pod security policy controller before defining the policies, you just command that nothing is allowed to be happened. In GKE, the pod security policy controller is disabled by default. If you choose to use pod security policies, first define them, and then enable the controller with the gcloud command shown here. Name represents the name of your cluster. You can take additional security measures to reduce how many of these are there especially if you choose to run recent versions of Kubernetes. For example, GKE's default policy is container optimized OS unlike the general purpose management the container optimized OS implements redundant file storage, performs system integration, and implements firewalls, automating and offline Anyone knows attacks all the update necessary. You can choose to run private clusters, which contain no without external engagements. You can also choose to run a cluster control plane for a private cluster without a public engagement. By default, private clusters do not allow private IP addresses to pass through public network. Using private clusters will authorize networks to make your cluster only by specific IP address ranges that you choose. Note that in your cluster Vpc network is your IP control plane, and so you can determine which jobs that manage your network. Don't forget to manage crypto security for sensitive virtual environment storage. Whenever possible, grant privilege and
In this lab, we will create namespaces within a G8 cluster, and then use role-based access control to permit a non-admin user to work with pods in a specific namespace. You'll learn how to create namespaces for users to control access to cluster resources, and create roles and role bindings to control access within a namespace. You learn how to understand the structure of GCP identity and access management access controls, and define cloud IAM roles and policies for Kubernetes engine cluster administration. Also learn how to use Kubernetes authentication and authorization to control who is able to do which things on the objects in your clusters. You learn how to manage access to resources and namespaces using Kubernetes RBAC rules. You learn how to control access to cluster scoped resources using Kubernetes RBAC cluster rules and cluster role binding. And you learn how to configure permission control to enforce specific security-related attributes for pods using Kubernetes pod security policies. Hi, I'm Soumya. Welcome to the Google Kubernetes Engine, or GKE, logging and monitoring module. In this module, you'll learn how logging is implemented in Kubernetes and how GKE extends that basic functionality using Stackdriver. Stackdriver is a suite of multi-cloud resource reconnaissance tools provided by Google that includes monitoring, logging, and debugging for your applications and infrastructure. In this module, you'll learn how to use Stackdriver to monitor and manage the availability and performance of your GCP resources and applications that are built with those platforms. Locate and inspect Kubernetes logs produced by resources inside your GKE clusters. Use Stackdriver and Google BigQuery for longer-term retention and forensic analysis of the logs that are produced by GKE and the Kubernetes resources inside your GKE clusters. How to monitor system and application performance from different vantage points, and how to create roles for wellness checks on the applications you're running.
Let's start by exploring the VPC. The objects by looking at projects, networks, and subnetworks. Projects are the key organizer of infrastructure resources in GCP. A project associates objects and services with billing. Now, what's unique is the fact that projects actually contain entire networks. The default quota for each project is 5 networks, but you can simply request additional quota using the GCP console. These networks can be shared with other projects, or can be peered with networks in other projects, both of which we'll cover in a later module. These networks do not have IP ranges, but are simply a construct of all of the individual IP addresses and services within that network. GCP's networks are global, spanning all available regions across the world, as shown earlier. So you can have one network that literally exists anywhere in the world, Asia, Europe, Americas, all simultaneously. Inside a network, you can segregate your resources with regional subnetworks. I just mentioned that there are 3 different types of networks: default, auto, and custom. Let's explore these types of networks in more detail. Every project is provided with a default VPC network with predefined subnets and firewall rules. Specifically, a subnet is allocated for each region with non-overlapping CIDR blocks. Also, each default network has a default firewall rule. These rules are configured to allow ingress traffic for ICMP, RDP, and SSH traffic from anywhere, as well as ingress traffic from within the default network for all protocols and ports. An auto mode network also has 1 subnet per region. The default network is actually an auto mode network. Now, these automatically created subnets use a set of predefined IP ranges with a /20 mask that can be expanded to a /16 mask. All of these subnets fit within the 10.128.0.0/9 CIDR block. As new GCP regions become available, new subnets in those regions are automatically added to auto-mode networks using an IP range from that block. A custom mode network does not automatically create subnets. This type of network provides you with complete control over its subnets and IP ranges. You decide which subnets to create in regions you choose, and using IP ranges you specify within the RFC 1918 address space. These IP ranges cannot overlap between subnets of the same network. Now, you can convert an auto mode network to a custom mode network to take advantage of the control that custom mode networks provide. However, this conversion is one way, meaning that custom mode networks cannot be changed to auto mode networks. So, you want to carefully review the configurations for auto mode networks to help you decide which type of networks meets your needs. On this slide, we have an example of a project that contains 5 networks. All of these networks span multiple regions across the world, as you can see on the right-hand side. Each network contains separate virtual machines, A, B, C, and D. Because VMs A and B are in the same network, network 1, they can communicate over internal IP addresses, even though they are in different regions. Essentially, your virtual machines, even if they exist in different locations across the world, take advantage of Google's global fiber network. Those virtual machines appear as though they're sitting in the same rack when it comes to a network configuration protocol. VMs C and D, however, are not in the same network. Therefore, by default, these VMs must communicate over external IPs, even though they are in the same region. The traffic between VMs C and D isn't actually touching the internet, but is going through the Google Edge routers, which have different billing and security ramifications that we're going to explore later. Because VM instances within a VPC network can communicate privately on a global scale, a single VPN can securely connect your on-premises network to a GCP network as shown in this diagram. Even though the 2 VM instances are in separate regions, namely US West 1 and US East 1, they leverage Google's private network to communicate between each other and to on-premises networks using a VPN gateway. This reduces cost and network management complexity. I mentioned that subnetworks work on a regional scale. Because a region contains several zones, subnetworks can cross zones. This slide has a region, Region 1 with 2 zones, Zone A and Zone B. Subnetworks can extend across these zones within the same region, such as Subnet 1. The subnet is simply an IP address range, and you can use IP addresses within that range. Notice that the first and second address in the range, .0 and .1, are reserved for the network and the subnet's gateway respectively. This makes the first and second available addresses, .2 and .3, which are assigned to the VM instances. The other reserved addresses are the second to last address in the range and the last address, which is reserved as the broadcast address. To summarize, every subnet has 4 reserved IP addresses in its primary IP range. Now, even though the 2 virtual machines in this example are in different zones, they will still communicate with each other using the same subnet IP address. This means that a single firewall rule can be applied to both VMs, even though they are in different zones. Speaking of IP addresses of a subnet, Google Cloud VPC lets you increase the IP space of any subnets without any workload shutdown or downtime. This diagram illustrates a network with subnets that have different subnet masks, allowing for more instances in some subnets than others. This gives you flexibility and growth options to meet your needs, but there are some things to remember. The new subnet must not overlap with other subnets in the same VPC network in any region. Also, the new subnets must stay inside the RFC 1918 address space. The new network range must be larger than the original, which means the prefix length must be smaller in number. In other words, you cannot undo an expansion. Now, Now, auto-mode networks start with a /IP range. They can be expanded to a /16 IP range, but no larger. Alternatively, you can convert the auto-mode network to a custom mode network to increase the IP range further. Also, avoid creating large subnets. Overly large subnets are more likely to cause CIDR range collisions when using multiple network interfaces and VPC network peering, or when using a VPN or other connection to an on-premise network. Therefore, do not scale your subnet beyond what you actually need.
You can also migrate a VM instance from one network to another. In the case of a VM that is connected to more than one network using multiple network interfaces, this process updates one of the interfaces and leaves the rest in place. The following migrations are supported: from a legacy network to a VPC network in the same project, from one VPC network to another VPC network in the same project, from one subnet of a VPC network to another subnet of the same network, from a service project network to the shared network of a shared VPC host project. In all cases, the VM stays in the region and zone where it was before. Only the attached network changes.
Let me show you how to expand a subnet within GCP. I've gone ahead and created a custom subnet here with a /29 mask, and a /29 mask provides 8 addresses, but 4 of those are reserved, leaving me with another 4 for my VM instances. So I can click in here, and you'll see that I already have 4 VM instances. So let's try to create another VM instance in this subnet. Now the subnet is in US West 1, so I'm going to go create an instance and specify the region for that. Without changing anything else, I'm just going to try and click create. Right, so as we can see, I did not get a green check mark next to my instance. Instead, I get an exclamation sign. And if I hover over that, I get the actual error that the IP space of this specific subnet has been exhausted. So as expected, I can only create 4 VM instances with a /29 mask. But I want to show you how to expand that. So let's go ahead and go to the subnet. And I'm going to directly click on my subnet. And click the edit icon up here to now change this address range. So let's, for example, change that to a /24. That's going to allow over 200 instances in here. And I'm just going to click save. I'm doing all of this without taking any of my VM instances down. And we can see up here in the notification that this is currently being updated. And we can see here that it's now reflected. I now have the /24. So let's go back to my instance page. And what I'm going to do is I'm actually just going to hit this retry button over here to see if I can recreate that instance within that subnet now that I've expanded it. Alright, so we can see that the instance has been created successfully and it's running. And that's how easy it is to expand a subnet in GCP without any workload shutdown or downtime. Now that we've covered GCP networks at a high level, let's go deeper by exploring IP addresses.
In Google Cloud, each virtual machine can have 2 IP addresses assigned. One of them is an internal IP address, which is going to be assigned via DHCP. Every VM that starts up and any service that depends on virtual machines gets an internal IP address. Examples of such services are App Engine and Google Kubernetes Engine, which are explored in other courses. When you create a VM in Google Cloud, its symbolic name is registered with an internal DNS service that translates the name to an internal IP address. DNS is scoped to the network, so it can translate web URLs and VM names of hosts in the same network, but it can't translate host names from VMs in a different network. The other IP address is the external IP address, but this is optional. If your device or your machine is externally facing, you can assign an external IP address. That external IP address can be assigned from a pool, making it ephemeral, or it can be assigned a reserved external IP address, making it static. If you reserve a static external IP address and do not assign it to a resource such as a VM instance or a forwarding rule, you are charged at a higher rate than for static and ephemeral external IP addresses that are in use. You can use your own publicly routable IP address prefixes as Google Cloud external IP addresses and advertise them on the internet. In order to be eligible, you must own and bring a /24 CIDR block or larger.
I just mentioned that VMs can have internal and external IP addresses. Let's explore this in the GCP console. So I'm going to go ahead here and try to create a VM. And I'm just going to leave all these as the default. But what I want to focus on is the networking interface. So I'm going to expand this menu right here and click on networking. So here we see that this is currently being created in the default network. We see the exact subnetwork, and that matches the region that I've chosen, which I just left to the default. And specifically, we see that this has a /20 mask here, and that really allows for a lot of addresses. Actually, 4,096 addresses to be exact, and 4 of those you can't use, so you'll be able to create over 4,000 VM instances in this subnet. So let me go ahead now. If I focus on the primary internal IP, you can see this is by default ephemeral. I could also custom input an internal IP address, or I could actually reserve one, meaning that if I restarted and stopped this VM, I'd still have the same IP. The same goes for the external IP. And moreover here, I actually don't even need an external IP. So as I just mentioned, only internal IPs are required for VM instances. I could actually say that I don't want an external IP address altogether. But let's leave that for now, and let me just create this instance to show you the internal and external IP addresses that get generated. Alright, so here we are. The instance has been created. You can see I have the internal IP address, and that is within that subnet mask that we just looked at. And I also have the external IP address. Now, I want to prove to you this external IP address is ephemeral. And the way I'm going to do that is I'm just going to click on this instance. I'm going to stop it. Alright, so here we can see that the instance has now been stopped. The internal IP address is actually still here, but the external IP address is gone. And if I now go ahead and restart that, it's going to ask me if I'm sure I want to do that because I get billed for that. Yes, I do want to restart this instance. We're now going to wait for that instance to start back up. And here we go. The instance is starting, but we can already see that the external IP address is now different. So this demonstrates that every VM needs an internal IP address, but external IP addresses are optional, and by default, they're ephemeral. Regardless of whether you use an ephemeral or static IP address, the external address is unknown to the OS of the VM. The external IP address is mapped to the VM's internal address transparently by VPC. I am illustrating this here by running ifconfig within a VM in GCP, which only returns the internal IP address. Let's explore this further by looking at DNS resolution for both internal and external addresses. Let's start with internal addresses. Each instance has a hostname that can be resolved to an internal IP address. This hostname is the same as the instance name. There's also an internal fully qualified domain name, or FQDN, for an instance that uses the format shown on the slide. If you delete and recreate an instance, the internal IP address can change. This change can disrupt connections from other compute engine resources, which must obtain the new IP address before they can connect again. However, the DNS name always points to a specific instance, no matter what the internal IP address is. Each instance has a metadata server that also acts as a DNS resolver for that instance. The metadata server handles all DNS queries for local network resources and routes all other queries to Google's public DNS servers for public name resolution. I previously mentioned that an instance is not aware of any external IP address assigned to it. Instead, the network stores a lookup table that matches external IP addresses with internal IP addresses for the relevant instances. For more information, including how to set up your own resolver on instances, please refer to the link below this video. Now let's look at external addresses. Instances with external IP addresses can allow connections from hosts outside of the project. Users can do so directly using the external IP address. Public DNS records pointing to instances are not published automatically. However, admins can publish these using existing DNS servers. Domain name servers can be hosted on GCP using Cloud DNS. This is a managed service that is definitely worth exploring. Let's look at it in more detail. Cloud DNS is a scalable, reliable, and managed authoritative domain name system, or DNS service, running on the same infrastructure as Google. Cloud DNS translates requests from domain names like google.com into IP addresses. Cloud DNS uses Google's global network of anycast name servers to serve your DNS zones from redundant locations around the world, providing lower latency and high availability for your users. High availability is very important because if you can't look up a domain name, then the internet might as well be down. That's why GCP offers a 100% uptime service level agreement, or SLA, for domains configured in Cloud DNS. For more information on this SLA, please refer to the link below the video. Cloud DNS lets you create and update millions of DNS records without the burden of managing your own DNS servers and software. Instead, you use a simple user interface, command line interface, or API. Another networking feature of GCP is Alias Ip Ranges. Alias Ip Ranges lets you assign a range of internal IP addresses as an alias to a virtual machine's network interface. This is useful if you have multiple services running on a VM and you want to assign a different IP address to each service. In essence, you can configure multiple IP addresses representing containers or applications hosted in a VM without having to define a separate network interface. You just draw the alias IP range from the local subnet's primary or secondary CIDR ranges. This diagram provides a basic illustration of primary and secondary CIDR ranges and a VM alias IP ranges. For more information on alias IP ranges, please refer to the link below the video. So far, you've learned about projects, networks and subnetworks, and IP addresses. Let's use what you learned to understand how GCP routes traffic and establishes firewall rules. By default, every network has routes that let instances in a network send traffic directly to each other, even across subnets. In addition, every network has a default route that directs packets to destinations that are outside the network. Although these routes cover most of your normal routing needs, you can also create special routes that override these routes. Just creating a route does not ensure that your packets will be received by the specific next hop. Firewall rules must also allow the packet. The default network has pre-configured firewall rules that allow all instances in the network to talk with each other. Manually created networks do not have such rules, so you must create them as you will experience in the first lab. Routes match packets by destination IP addresses. However, no traffic will flow without also matching a firewall rule. A route is created when a network is created, enabling traffic delivery from anywhere. Also, a route is created when a subnet is created. This is what enables VM on the same network to communicate. This slide shows a simplified routing table, but let's look at this in more detail. Each route in the routes collection may apply to one or more instances. A route applies to an instance if the network and instance tags match. If the network matches and there are no instance tags specified, the route applies to all instances in that network. Compute Engine then uses the routes collection to create individual read-only routing tables for each instance. This diagram shows a massively scalable virtual router at the core of each network. Every virtual machine instance in the network is directly connected to this router, and all packets leaving a virtual machine instance are first handled at this layer before they're forwarded to the next hop. The virtual network router selects the next hop for a packet by consulting the routing table for that instance. GCP firewall rules protect your virtual machine instances from unapproved connections, both inbound and outbound, known as ingress and egress respectively. Essentially, every VPC network functions as a distributed firewall. Although firewall rules are applied to networks as a whole, connections are allowed or denied at the instance level. You can think of the firewall as existing not only between your instances and other networks, but between individual instances within the same network. GCP firewall rules are stateful. This means that if a connection is allowed between a source and a target, or a target and a destination, all subsequent traffic in either direction will be allowed. In other words, firewall rules allow bidirectional communication once a session is established. Also, if for some reason all firewall rules in a network are deleted, there is still an implied deny all ingress rule and an implied allow all egress rule for the network. You can express your desired firewall configuration as a set of firewall rules. Conceptually, a firewall rule is composed of the following parameters. The direction of the rule. Inbound connections are matched against ingress rules only, and outbound connections are matched against egress rules only. There's the source of the connection for ingress packets, or the destination of the connection for egress packets. The protocol and port of the connection, where any rule can be restricted to apply to specific protocols only, or specific combinations of protocols and ports only. The action of the rule, which is to allow or deny packets that match the direction, protocol, port, and source, or destination of the rule. The priority of the rule, which governs the order in which rules are evaluated, where the first matching rule is applied. And the rule assignment. By default, all rules are assigned to all instances, but you can assign certain rules to certain instances only, as we will explore in more depth in the next module. Let's look at some GCP firewall use cases for both egress and ingress. Egress firewall rules control outgoing connections originated inside your GCP network. Egress allow rules allow outbound connections that match specific protocol ports and IP addresses. Egress deny rules prevent instances from initiating connections that match non-permitted port, protocol, and IP range combinations. For egress firewall rules, destinations to which a rule applies may be specified using IP CIDR ranges. Specifically, you can use destination ranges to protect from undesired connections initiated by a VM instance towards an external host, as shown on the left. You can also use destination ranges to prevent undesired connections from internal VM instances to a specific GCP CIDR range. This is illustrated in the middle, where a VM in a specific subnet is shown attempting to connect inappropriately to another VM within the same network. Ingress firewall rules protect against incoming connections to the instance from any source. Ingress allow rules allow specific protocol ports and IP addresses to connect in. The firewall prevents instances from receiving connections on non-permitted ports and protocols, and rules can be restricted to only affect particular sources. Source side ranges can be used to protect any instance from undesired connections from either external networks or from GCP IP ranges. This diagram illustrates a VM receiving a connection from an external address and another VM receiving a connection from a VM in the same network. You can control ingress connections from VM instance by constructing inbound connection conditions using source-side ranges, protocols, and ports.
Hierarchical firewall policies let you create and enforce a consistent firewall policy across your organization. You can assign hierarchical firewall policies to the organization as a whole or to individual folders. These policies contain rules that can explicitly deny or allow connections, as do virtual private cloud VPC firewall rules. In addition, hierarchical firewall policy rules can delegate evaluation to lower-level policies or VPC network firewall rules with a go-to-next action. Lower-level rules cannot override a rule from a higher place in the resource hierarchy. This lets organization-wide admins manage critical firewall rules in one place. By default, all hierarchical firewall policy rules apply to all VMs and all projects under the organization or folder where the policy is associated. However, you can restrict which VMs get a given rule by specifying a target network or target service account. The levels of the hierarchy at which firewall rules can now be applied are represented in the diagram shown here. The yellow boxes near the top represent hierarchical firewall policies, while the blue boxes at the bottom represent VPC firewall rules.
Let's apply some of the network features we just discussed in a lab. In this lab, you create an auto-mode VPC network with firewall rules and 2 VM instances. Then you explore the connectivity for those VM instances. In this lab, you explored the default network along with its subnets, routes, and firewall rules. You deleted the default network and determined that you cannot create any VM instances without a VPC network. So you went ahead and created a new automated network with subnets, routes, firewall rules, and 2 VM instances. Then you tested the connectivity for the VM instances and explored the effects of the firewall rules on connectivity. Let me walk you through the lab. Now, keep in mind that GCP's user's interface can change, so your environment might look slightly different. So here I am in the GCP console, and the first thing that I'm going to do is just take a look at the subnets. So to do that, I'm going to click on the navigation menu, and I'm going to look for VPC networks, and then click on VPC networks. So here we can see the default network, and you can see that there's a subnet for each of the different regions in which GCP has data centers. We can also see that each of these is in a private address space. That is the RFC 1918 CIDR block. I can also look at the routes by clicking over here. And these were automatically established. So we can see a route to the default internet gateway. And then there's also a route for each of the individual subnets within the default network. Now I can also view the firewall rules. We're going over here, and these are all here by default. There is an allow ICMP firewall rule and allow internal firewall rule. This allows connections on all protocols and ports. There's a rule to RDP, or remote desktop connection, and one for SSH. Now, what I'm going to do is I'm going to delete this network. So I'm going back to VPC Networks. I'm going to click on Default. I'm going to click Delete VPC Network. I'm going to have to confirm that I want to delete that. And this is going to take a couple seconds now. You can see the progress right here. And anytime you're doing anything in the GCP console, you'll see that you get notifications up here that tell you what's currently ongoing. So you see that this operation is actually in process right now, and we'll get a notification when this has actually been completed. So we can now see that the VPC network has been deleted, and I can click on the notification and see that that has just been completed. Now, we'll also see that if I go into the route section now, that there are no longer any routes because there's no network for those routes. And if I also go to the firewall rules, there are no firewall rules because those are attached to a network. So let's try and create a VM instance. If I go back to the navigation menu and scroll up, I'll find Compute Engine. I can click on that. And in here I'm going to click Create Now to create an instance. I can leave all of these defaults, but if I down here expand this menu option, Management, Security, Disk, Networking, and Sole Tenancy, and click on the Networking tab, you see that I actually get an error and it says there are no local networks available right now. Okay, so as expected, I cannot create a VM instance without a VPC network. So what we're going to do now is we're going to recreate that automatic created network that was in there. And that's pretty simple. I just go back to the VM instances page and then scroll for VPC networks. And I'm going to create a VPC network. Now I can give that network a name, so I can just call that my network. And then I have the option to choose between the custom mode or the automatic mode network. And in this case, I'm going to choose the automatic mode network. And again, what that means is that a subnet will be created for each of the different regions, as you can see right here. Now, I can also create some default firewall rules directly. These are the exact ones that we saw before. But instead of being applied to the default network, they're now applied to this new network that I'm creating. So I can just directly select these. And you also see there is the implied deny all ingress and the allow all egress rules. They're directly in here too. So I'm going to go ahead and now create this network. And again, there's an action now being performed in the console. So I can see there's a progress, and if I go to notifications, I can also see that I'm currently creating a network in here. So now we can see that the my network has been created, and just like before, I have subnets for all of the individual regions. I could also go to routes and see that I have all these routes, and the firewall rules that I selected earlier are also visible just here. So let's go ahead now and try to recreate a VM instance. So for that, I'm going to head back to Compute Engine and click on Create. And let me give this instance a name. So this is in the network, my network. So I could use that as a name. I could specify this is in the US and just say that specifically this is a VM. I can choose the region and zone, and I can modify the machine type. In this case, I'm fine with a micro, so I'm just going to click that. And now I can go ahead and create that instance. So I can hide this info panel now. We can see that this VM has been created. What we can also see is the internal IP address. So if we look at this, this is in the 10.128.0.2. I mentioned earlier that .2 would be the first address that can be used. And we can also see, if I click on NIC0, that this is part of the My Network. And specifically, it is in the zone that I specified, and it gets its IP address range from the subnet that is related to that zone. So let me go ahead and create another VM instance. I can just click on this plus icon right here, and let me create this one, for example, in Europe. So I'm going to say the name is MyNet EU VM, and I can specify the region as Europe West 1, and you see directly that this is located in Belgium. And then I could choose a zone. And again, I don't need a very powerful machine. A micro machine, which has a shared virtual CPU, is more than enough. And then I again can click on Create. So we can see that this VM has now been created. And again, this internal IP address here, the first usable address is .2. And I can click on here to verify this is part of my network. And specifically, it's the subnetwork that covers the Europe West 1 region. Now, the external IP addresses that are in here, they're actually both ephemeral. What that means is if I stop one of these instances and then restart it, it will actually assign a new address. I can change that if I want to, but I would have to assign a static external IP address, and there's actually a cost associated to that. So I'm not going to do that right now. Now, both of these instances are on the same network, so ideally I should be able to communicate between these instances. So what I'm going to do now is I'm going to actually SSH into one of these instances, and I'm going to try to ping one of the other instances by using the external and internal IP addresses that I see right here. So what I'm going to do is on the machine in US Central 1, I'm going to click on SSH. I'm just going to wait for that connection to be established. And then what I'm going to do is I'm going to grab the internal IP address of the other VM instance. And I'm going to try to ping this machine. And I'm going to just do that 3 times and then paste the IP address. And so from here we can see that all of the packets were transmitted, they're all received, 0 packet loss, so I can communicate. And the reason I can do that is because these are both on the same network, and there's the default allow all internal firewall rule that I checked earlier. Now, let me repeat the same, but this time actually use the name of the instance. So I'm going to ping again 3 times. I'm going to use the name of the VM, MyNet EU VM. And this works as well. We can actually see that the fully qualified domain name here is actually what was ultimately reached. And this is very useful, especially if I restart instances, even the internal IP address is actually ephemeral. And with the fully qualified domain name, I can make sure that I can always reach this VM instance. Now, I can also get to the external IP address. So let me grab the external IP address now and come back. And instead of pinging the internal IP address, I'm going to ping that. And that works as well because of the allow ICMP firewall rule that we have. So currently I can ping internally as well as externally between these VM instances. Now, let me see if that's still the case if I remove some of the firewall rules. So I'm going to go back to VPC Networks. Firewall rules. And I'm going to select the ICMP rule, and I'm going to ask to delete that. And yes, I'm confirming. Alright, so now that the rule has been deleted, let me go back to my VM instance, which I still have open here, and try to ping the external IP address one more time.
So we can see that this is not really working. It's currently failing. I'm actually going to wait for it to time out, and there we go. It's telling me that 0 of the packets were received, meaning all of them were lost. I'm going to use my recall buffer in here to just ping the internal IP address one more time. And we can see that that still works, because I have that firewall rule that allows connections within my network, just not across the network anymore. Now similarly, I want to show the effect of deleting that firewall rule. So I'm going to go back, click on the allow internal rule, and delete that as well. Right, so now that that rule is deleted as well, let me go back to that instance and try to ping the internal IP address one more time. And as expected, we are no longer able to do that now. You can see that this is kind of hanging here, but it's going to give us an error in just a second and say that all the packets were lost. And there we go. So let me exit out of this instance. And now the last rule that we're going to delete is the SSH rule. Now I'm using Linux-based instances, so I'm using SSH. If you were using a Windows-based instance, you probably would want to delete the RDP instead. So let me delete this firewall rule. And now I'm going to go back to Compute Engine. And just click on SSH for any of these instances. It's going to pop up a window for me. And it's going to try that now a couple times. It's already a lot slower than we saw earlier, and it's going to give us several tries. And ultimately, we should be getting an error that it just can't connect to that specific port. So let's just wait for that to come up. Alright, so we can see that the connection has failed. We're unable to connect to the VM on port 22. So with that, we've successfully shown that these firewall rules do affect the VM instances and that you have full control over the access to those instances. Next, let's look at multiple network interfaces. VPC networks are by default isolated private networking domains. As I mentioned earlier, VM instances within a VPC network can communicate among themselves via internal IP addresses, as long as firewall rules permit. However, no internal IP address communication is allowed between networks unless you set up a mechanism such as VPC peering or VPN. Every instance in a VPC network has a default network interface. You can create additional network interfaces attached to your VMs through network interface controllers or NICs. Multiple network interfaces enable you to create configurations in which an instance connects directly to several VPC networks. Each of these instances must also have an internal IP address, and each interface can have an external IP address. For example, in this diagram you have two VM instances, and each instance has network interfaces to a subnet within VPC1, VPC2, and VPC3. Typically, you might require multiple interfaces if you want to configure an instance as a network appliance that does load balancing, intrusion detection and prevention, web application firewall, or WAN optimization between networks. Multiple network interfaces are also useful when applications running in an instance require traffic separation, such as separation of data plane traffic from management plane traffic. Now, there are some limitations that I want you to remember when creating VM instances with multiple network interfaces. First, you can only configure a network interface when you create an instance. Each network interface configured in a single instance must be attached to a different VPC network, and each interface must belong to a subnet whose IP ranges do not overlap with the subnets of any other interfaces. The additional VPC networks that the multiple interfaces will attach to must exist before you create the instance. You cannot delete a network interface without deleting the instance. When an internal DNS query is made with the instance hostname, it resolves to the primary interface or NIC0 of that instance. if the NIC0 interface of the instance belongs to a VPC network different from the VPC network of the instances using the internal DNS query, the query will fail. You will explore this in an upcoming lab. Now, the maximum number of network interfaces per instance is 8, but this depends on the instance's machine type, as shown in this table. Instances with less than or equal to 2 virtual CPUs can have up to 2 virtual NICs. This includes the F1 Micro, G1 Small, the N1 Standard 1, and any other custom VMs with 1 or 2 virtual CPUs. Instances with more than 2 virtual CPUs can have 1 NIC per virtual CPU with a maximum of 8 virtual NICs. Let's apply the multiple network interface concepts that we just discussed. In this lab, you create several VPC networks and VM instances and test connectivity across networks. Specifically, you create 2 custom mode networks, Management Net and Private Net, with firewall rules and VM instances as shown in this network diagram. The MyNetwork network with its firewall rules and 2 VM instances, MyNet UVM and MyNet USVM, have already been created for you in this lab. In this lab, you created several custom mode VPC networks, firewall rules, and VM instances using the GCP. Console and the Gcloud command line. Then you tested the connectivity across VPC networks, which worked when pinging external IP addresses, but not when pinging internal IP addresses. So you went ahead and created a VM instance with 3 network interfaces and verified internal connectivity for VM instances that are on the subnets that are attached to the multiple interface VM. Let me walk you through this lab. Now, keep in mind that GCP's user interface can change, so your environment might look slightly different. Alright, so here I am within the GCP console, and the first thing I'm going to do is create the Management Network. So I'm going to go to the navigation menu, look for VPC networks, and you'll notice here that there's already the default network, but we've also gone ahead and created the MyNetwork network for you in here. So I'm going to click on Create VPC Network. I'm going to give it a name. Now this is a custom mode network, so I'm going to leave this as custom. And then I'm going to use the provided name for the subnet. I'm going to place this into US Central 1. And I also have an IP address range already that I can just go ahead and use. So I'm going to click done on this. But the interesting thing is when you use the GCP console, you can actually ask for the equivalent command line. So let me click on that here. And this is pretty useful if you wanted to create what I just did from the command line, which is actually what you're going to do for the next network. So let me close that and create it through the GCP console. Now this is creating in the background, but I can actually already start and create the next one. And for this one, I'm going to use the command line. And to do that, I'm going to activate the Google Cloud Shell. And the icon for that is right here. I'm prompted if I want to start Cloud Shell. I'm going to say yes. sometimes it's actually useful to put this in a different tab. So I'm going to go ahead and just put this in a different tab, and that way I can go back and forth in between Cloud Shell and the GCP console. Now, I'm going to use a command that we provided you with in the lab. So this is going to create a network. It's going to call it private net, and it's going to be a custom mode network. So I'm now just going to wait for this to complete in here. So here I got a message that this has now been completed, and now I'm going to create the first subnet, that is the private subnet in the US. So specifically I'm giving it a name, specifying the region, and again a range. Alright, so here I can see that the subnet has been created. I'm going to create one more. This one is in Europe West 1, and I also have an IP address range for that. Okay, so here we can see that the other subnet has been created as well. Now, from Cloud Shell, I can actually also just query all of the networks. The command for that is gcloud compute networks list. And if I run that, I should getting returned the 4 networks. There's the default auto network and the my network, which was also auto, which was already there before, and the 2 custom mode networks that I created. Now, for the custom mode networks, I only created a subnet for one of them and 2 for the other, but the auto mode networks have a subnet in each region. And I can also just list all of those subnets and sort them by network. And so here you could also in Cloud Shell directly see all of these. So I have all of the ones sorted by the default. There's the management net, which was only one subnetwork. There's the auto mode network, my network. And then I have the 2 subnets here for the private net network. Now, let me go into the GCP console and verify that I see the same thing here. So I'm going to click back. Here's the default mode network. Here's that one subnet in management net, the auto mode network, my network, and the 2 subnets in private net. So the information is the same. It's purely a question of if you prefer using a user interface or if you want to query for your networks. So now I'm going to go ahead and create some firewall rules for the management net network. So I'm going to click on firewall rules, click on create. I can give this a name, and I can actually put several protocols and ports into one firewall rule. So this rule will allow ICMP, SSH, and RDP so that I don't have to create 3 separate rules. Now I want to attach this to the management net network, so I'm going to select that. And I want this to apply to all of the instances within the network. Now I need to define the source IP ranges, and I'm just going to say connection established from anywhere. And the important thing here is to include the /0. Now the key now is to provide the actual protocols and ports combination. So obviously I want ICMP, and then for SSH I want TCP22, and for RDP I want TCP 3389. So I'm going to go ahead and create that in a second, and again here you can get the equivalent command line. So if I click on that, you can see that this is very straightforward to create from Cloud Shell if we want to. And we're actually going to do that for the next firewall rule. So let me go ahead and create this. And now what I'm going to do is I'm going to return to Cloud Shell. And I'm going to create the same firewall rule, but this time for the private net network. So let me put that in here. Has the exact same rules, has the name of the network, what the action is, the rules, as well as the source ranges. So I'm going to click enter on that, and I get a little action here that's showing me that this firewall rule is being created. Alright, so I'm getting a message that the firewall rule has been created, and I could actually query all of the firewall rules right now and sort that by network. So I can see here are my different firewall rules. can actually go back to the console and verify that I see the exact same rules here by sorting by network as well. So 4 for the default, 1 for management net, 3 for my network, and private net is not showing up yet. That can sometimes happen. So if I click refresh, you can see that private net is now in here. And the reason that was is because I created this other one from Cloud Shell, and this window was just not refreshed in between. So now I'm going to go ahead and create some VM instances. So let me go ahead and go to the compute engine section. I'm going to create these for each of the custom mode networks. Now when I come here, you see I already have 2 instances that are part of the My Network. And these have already been created for you. So let me create some more instances. I'm going to define a name, region, the machine type I'm just going to leave as is. Now what's important is that I specify the network. So I'm going to expand the setting right here, go to the networking tab, and you see this would have actually created this in the default network. But I want to create this in the management network. So I'm going to select it. It's also going to directly select the subnetwork, because this is the only subnetwork that is in the region that I've selected. So let me leave that as this. And click Done. And once again, I get an equivalent command line. So if I click on that, this is a little longer. There are some very specific pieces in this. You'll actually see that we don't need all of this. We could just use some of the defaults. But let's go ahead and create this and then try to repeat the same from Cloud Shell for the other network. So while this is being created, I'm going to hop over to Cloud Shell, and the command to create an instance, I just specify the name, the zone, the machine type, and the subnet. So let me hit enter on that. So we can see the instance has been created. We can also now query in here for all the instances and sort those by zone. And I'll see here are my 4 different instances. One of them is in Europe, and the other ones are all in US Central 1. I can see the same if I go back to the GCP console. I'm just going to have to refresh here fast because the instance that was created. Now, currently you see that the network is not being displayed here. But if I collapse this,
also when the data is relationally structured. In other words, this is naturally represented by one or more tables of columns and rows. We could be identifying search network without cloud by a simple choice. Its no-sequence orientation gives you the best tables to represent your data in a way that's best for your application. On the other hand, if your data is relational, now ask yourself whether you need to maintain a relative space horizontally. Horizontal space and global transaction existence are the key benefits of cloud span. You don't access your database going beyond the direct page. And classic scaling strategies for relational databases such as replicas should be clear. Then you go horizontal cloud span expansions. Now let's get into addition. Ask yourself whether you need to database by adding a message processing based updates and loading associated websites of the database. Cloud web table is a good choice. Otherwise, assuming your analytics workloads are more oriented towards noise contributions based on stream data, BigQuery is a good that concludes using GCP managed storage services with Kubernetes Engine. In this module, you learn how to recognize the closing parts of managed storage services versus self-managed containerized storage. Identify use cases for cloud storage for applications running in a Kubernetes cluster. Identify the range of GCP managed database services and how to use Cloud SQL proxy to simplify the task of connecting to Cloud SQL from within Kubernetes applications.
Keep in mind that features that are available